Okay, so let's start with the last talk. So the last talk is and the speaker. And it's a joint work with Christian Blum, Pedro Pinacho, and Manuel López Ibáñez, that now is in Valladolid, in Malaga, by the way. No, it's in Malaga. And it's a paper where it's a work where we try to design a general algorithm to solve combinatorial optimization problems. Okay, that was the idea. The main work was carried out by Christian, and most of the merits are have to be given to Christian. Okay, and now it's in Barcelona in the specific Institute of Artificial Intelligence. Christian. He was in the Basque Country as a. So that's the idea. The idea is to generate a general algorithm to solve combinatorial optimization problems. Okay, who are familiar with combinatorial optimization problems? You are familiar, you are also familiar. The rest of you, you are not familiar with combinatorial optimization problems. Oh my God, so that's going to be difficult. So basically, a combinatorial optimization problem is the Charlie-Seisman problem. No, everyone knows the Charlie-Seisman problem. No, yeah, okay. And there are two different ways to solve this problem. One way is to use exact algorithms. Okay, one can use exact algorithm like Branch and Bound, Branch and Cut, this kind of algorithms. The problem is that when the size of the problem starts to increase, the algorithm never finishes. Okay, and that's a problem. Another way is to use meta-heuristic algorithms. Meta-heuristic algorithms are general methods that they use, let's say, affordable computational time, but however, there is no guarantee of convergence. Okay, so when he was using a genetic algorithm, he found a good solution, but there is no guarantees to be optimal solution. Okay, so the question is, can we combine the best of both worlds and define a hybrid algorithm? And this is one of the objectives of this paper. Try to combine elements from meta-heuristic algorithms and elements from exact algorithms and to design an algorithm that combines both. Of course, when you use meta-heuristics, it's clear that you have no convergence guarantees. Okay? In fact, simulated annealing is one of the meta-heuristic algorithms, and it comes with convergence guarantees, but you have to wait longer and longer and exponential time. You have to wait an exponential time. So, I mean, it converges, but what's the point with that? So the algorithm is really, really easy. It has two steps. First of all is to construct a subinstance from the instance you want to solve. You want to solve a problem, and instead of solving a problem, you construct a subinstance of the problem. Okay, a reduced version of the problem. You use an exact algorithm to solve the instance, and then you repeat the process several times. Okay, that's it. It's a very, very simple idea. It's a very simple idea, and it works quite well in the examples where we have used the idea. So the first thing we have to do is to construct a subinstance. Okay, this is a little bit weird how to construct a subinstance, but we want to see with an algorithm and with an example, and you will understand. Okay, the second thing is to solve and then to repeat the previous step. We will come back to repeat. So imagine we have a TSP problem, Charlie-Seisman problem, and we want to solve the Charlie-Seisman problem. Okay, so in order to construct, for instance, one way to construct a subinstance of the problem is to find different solutions. Okay, so imagine I can find a solution in the following way. This solution is not going to be the optimal solution. It's going to be one possible solution that with high probability is not the optimal solution. I start in C1, and then, for instance, what I can do is to go to the closest point, that is C4. From C4, I can go to the closest point. These are the different distances. So the closest point is C5. Then I can go to the closest point and so on. And then I have a possible solution to the problem. Okay. If we take these arcs if we take these arcs, then I have a subinstance of the problem. It's a really easy subinstance. I mean, if I only consider these possible arcs, then I have a subinstance of the problem, but it's a really simple subinstance. It has only one solution. However, if I repeat this process randomly, so instead of going here, I go with some probability that is inversely proportional to the other nodes and construct several solutions this way. No? I construct several solutions this way and take all the arcs that has appeared during this process of constructing the solution, then I have a sub-instance of the problem, okay? I have a subinstance of the problem. Instead of having n times n minus 1 divided by 2 arcs, I have a reduced number of arcs, a reduced number of components, but maybe the optimal solution contains these arcs. And then what I do is, the next thing that I do is to solve with an, well, here is the subinstance. It's a simple subinstance, okay? These are the components that are the edges. And then what I do is repeat the random ready process n8 times and then solve with a exact method, okay? So with a branch and bound. Of course, the problem is much easier to solve because the size of the problem is much smaller. Okay, the number of arcs is smaller, much smaller than the original number of arcs. And this is the idea. However, what I would like to do is to repeat this process several times. I'm not gonna do that only once, but I'm gonna do that several times. And what I'm gonna do to do that is to remember that the algorithm has here something like, wait a minute. It's called construct, search, merge, and adapt, okay? So the construct we have done, the search is solving, and then we have to do something with the merge and adapt. And the merge and adapt is the repeat the previous process, okay? So what we are gonna do is this. So in one step, I generate many solutions, create an instance, solve the instance. And then what I'm gonna do is repeat this process, but then taking into account the edges I have, I delete some edges, those that are old and have not been appeared in any real solution, in any optimal solution. I delete those, or delete those for some time and keep only those components that have participated in some optimal solution for a while. Okay? And that's the algorithm. I mean, it's nothing but that. Okay? Generate solutions, take the components, solve, delete some components, generate more solutions, add components, and so on. Okay, and this is the global idea of the algorithm. Okay, the good point is that the only thing that you need to solve, well, here is the algorithm. Okay, here's the pseudocode of the algorithm. Well, basically, you have a loop here. You generate new solution. For each solution generated, you added the components to the pool of components. Start with h equals 0, and then apply the exact solver. And then you adapt here, because what you do is delete those components that has been for a long time and have not participated in any optimal solution, and keep the others. Okay, so I keep a pool of components already. Yeah, and that's the idea. In order to apply the algorithm, the only thing that I need is a constructive heuristic, okay, a way to construct solutions, and a way to construct solutions adding components, okay, a way to construct solution adding components. In most of the cases, if you can codify the algorithm as if you can codify the algorithm as a binary integer programming, you have components because each variable can be considered as a component. So the algorithm is general enough to consider most of the problems, most of the combinatorial optimization problems we usually deal with in practice. So you need a constructive heuristic and an exact solver. This is the only thing. Okay? Any doubt?
I have one methodological doubt. So an instance of a problem for you is a solution or an algorithm to solve.
No, an instance of a problem is imagine you have the, yeah, that's important. An instance of a problem, it's a particular realization of a problem. Imagine the TSP, an instance of the TSP is a matrix with numbers, with a specific distances between CD1 and CD2. Okay?
So it is not the algorithm I will use, it's not the decision of
No. An instance, problems, algorithms. An instance is a particular realization of a problem. Okay? That's the idea. So when I construct sub-instances, I am reducing the instance. For instance, what I do is, if I have the matrix, the distance matrix of a TSP, what I do, in fact, is to put 0 to some of the distance. I do not consider, well, put minus infinite, no? I do not consider these edges anymore. I do not consider these edges anymore. Okay, that's it. Yep. That's clear? Yes, a really simple idea, but it works quite well. Okay, and now what I'm going to show you is an example. It's a little bit difficult. It's a little bit difficult on how to apply this algorithm. I mean, for illustration purposes, it would have been much easier to do with the TSP. But I have no, I mean, we didn't work with the TSP. So we did with more complex problems. And one of the problems we dealt with this minimum covering arborescence problem, that is, it's a little bit difficult to understand. So basically, we are given a directed graph, and this directed graph has some weights on the edges, okay, on the arcs, and there are some black nodes, and the goal is to find a tree that passes through, or that a tree that contains all the black nodes, and at the same time, it has the lowest possible weight. Okay, the lowest possible global weight. So it's clear. So basically, I have to find a tree that contains these 3 nodes, and in such a way that the weight of the edges is the lowest. And in this case, here you have a solution. Okay, this is a solution to the problem. The problem is more. I mean, it seems easy, but again, it's this kind of empty problems that are not that easy. Okay, this is a solution. So if we want to apply our this is called arborescence, our minimum arborescence problem. No, I don't know this. Okay, that's the problem. So if we want to apply our algorithm, we need to know which are the solution components. Okay, in our case, the solution components are the directed arcs. Okay, all the directed arcs in the original graph are the solution components. And a subset of arcs is a valid solution if they form a tree, and also they include the set of black nodes that we will denote by X. Okay, the set of nodes. So in order to apply our algorithm, the first thing we need is a probabilistic solution generation process. Okay, it's a constructive method for generating possible solutions. So the way to generate possible solution is to start in the first node, is to start in this node, and then choose one of these nodes. Okay, and then choose another node, and then choose another node, and so on. Okay. Of course, what we're going to try to do is to put those arcs that has the lowest value. Okay, we are trying to put those arcs that has the lower values. But at the same time, we want diversity. I mean, one way would be, okay, I just start here, I choose -4, then probably 3, then -2, then probably 1, and that's all. No, that would be a possible solution. It's a tree. If I go here, 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 it's a tree, and it's not too bad. Okay, but probably I also could choose this one I could also choose this one. So one way is to just try to find the lowest edge. But this would only give us one solution, and we need several solutions. So we need several solutions, and we need diversity. So in order to do that, we consider what we call a readiness value. So we have this delta is what we are going to call readiness value. So the readiness value tells me if I'm going to choose the best option or if I want to choose a random option. Okay. So I start in the first node, and then I go choosing nodes in the following way. First of all, choose a readiness value. Then for each possible node, consider only the arc with the minimum weight. So if I'm here, I'm not going to consider all the possible edges, only those. For continue from here, I only going to consider those with the minimum value. Okay. So in this case, this or this one or this one, but probably I should choose randomly in these two. Okay. And then I choose the node with the global minimum weight with probability delta, the greatness. Otherwise, with a probability inversely proportional to its weight, choose a node. Okay, so I try to combine choosing the best one, apparently the best one, with choosing randomly. Okay, so this is important. In most of the times, you want to have good components, but at the same time, diverse components. So you have to mix both things, good components and diverse components. Okay? So we repeat this step. We will repeat this step until there is no remaining nodes. And this is repeated n8 times. Okay? This process is repeated n8 times until we reach many solutions, n8 solutions. Not the times, okay. Then here we also need an IP program to be solved. Okay, once we have a sub-instance, we need to solve with the IP program. And here is the IP program. I mean, probably it's difficult to understand. So basically, this is the objective function. I try to minimize. XA tells me about when the edge A is in the solution or not. And we have different equations that tells me different information. I mean, you have to go through the edges in X. Okay, you have to go through the edges in X, and I mean, I could go through all of them, but I think no, I'm not gonna enter in this. Okay, so with these two things, we can apply the algorithm. Okay, and this is what we are gonna do. We are going to apply the algorithm, and in this case, we will do experiments. But the computational experience also like. Okay, so we are going to compare our algorithm, our proposal with two approaches. One is to repeat the greedy approach many times. Okay, and for each solution of the greedy approach, I take the best. Okay, so I would apply one possibility is to apply many times. Another is to just the application of Cplex to the original problem. Okay, I apply the Cplex to the original problem using this formulation, and then I also apply our algorithm. Okay, we generate the instances. Because even the problem has been has appeared in bioinformatics mainly. We have no at hand some instances. So we generate instances with different number of nodes, with different probabilities for generating the arc, with different proportion of nodes in the whole graph, and then the arc weights were obtained uniformly at random from this, and 1% uniformly at random from this, and globally we generate 270 instances. 10 instances for each possible configuration of the parameters. Okay. For the algorithm configuration, we use this tool that is called iRace that was proposed by one of the authors. It's a tool quite common. This was proposed by Manuel López Ibáñez. and we collaborate with him for the generation of the configuration of the parameters. And this, we consider NA is the number of solutions, the number of greedy solutions we obtain. So we consider different value. This is the time that a component is in the subinstance. This is the time that a component is in the subinstance. This is the greediness, or the values of the possible values of the greediness. And after applying arrays to some of the instance, we obtain these results. So what you can see is that, for instance, what we can see here is that when the instance is small, with n is small and the graph is sparse, we can generate quite a lot of instances. We can have quite a long time the components in the subinstances because it takes not much time. So and the greediness can be 0, so I can go all the time to the best one, and I have enough diversity. Okay. When we increase the complexity, then the thing changes. I am allowed to generate a small number. I'm allowed to generate a small numbers of solutions at each step. The time that the components are kept in the subinstance is small, and I need some kind of randomness. Okay, I need some kind of randomness. I need variety. And finally, you can see here the results. Sorry for this, but it was impossible to make it. Okay, I think I can make it bigger. Let's see if you can see something. Let's start here. So here are the results. Okay, this is the objective function value. Okay, this is the objective function value. This is the algorithm ready. This is the greedy algorithm. This is the triplex approach, and this is our approach. Okay, here you have the computational time. So as you can see here is the instances. Okay, this is the time, the size of the instances. So when the instances are small, the greedy works well. Okay, of course the triplex is able to find the optimal solution. Also our algorithm is able to find exactly the same solutions as the triplex. Okay, no, in all the cases, as you can see here that we were, however, the computational time of our approach is in general, here is still the triplex is competitive, but when the instances start to increase, it's not the case. In the last case, when the instance is 5,000, the triplex cannot finish, basically. It doesn't finish. And our algorithm became quite, well, it's able to finish, and it takes a time, okay, takes some computational time. But, and then when we increase, this is with only one, you have to go through 1% of the nodes, and when you have to go through 20% of the nodes, the results are quite similar, okay? Again, our algorithm is able to reach exactly the same values of the triplex. The greedy works really bad. And then when we increase the number of nodes, the triplex is unable to find a solution, and we are able to find. And also here, even the computational time of our approach is lower than the one of triplex. Even when we are really close in terms of computational, in terms of accuracy, okay, really close. I mean, it's here there is a 5 and we have a 1, so they are really close. So the computational results are really good. Okay, and just for finishing, more or less on time. So, so the idea is to propose a general framework for optimization. Okay. So a general idea that can be applied to many different problems, okay? And try to combine, I mean, we are really involved in trying to find good hybrid solution in which you have one meta-heuristic part, one exact part, and try to take the best of both worlds, okay? Well, it's easy to apply to a high variety of problems, and one of our goals is to extend to other problems. Okay, and that's all. Now what you can do is to ask me a lot of questions, just because I asked you a lot of questions. So it's your turn. Use.
I have one comment and one question. The comment is that I like very much those algorithms that they mix deterministic, I call them deterministic, but it's that part, and an heuristic part. Because I think that deterministic, when the right solution is detected, it gives efficiency, and heuristic gives exploratory stuff to find the correct solution. I like that very much. It's also what you did. The question is that I do not really understand why the solution, the real solution is found. The optimal solution.
You have no guarantees. I mean, the algorithm comes with no guarantees.
You can get suboptimal solution.
Yeah. The algorithm comes with no guarantees because you don't know if you are going. You are not sure if you are going to include in the subinstances one of the components that is in the optimal solution.
But how even no guarantees of feasibility?
Well, yeah, no. We have guarantees of feasibility because we generate solution. I mean, the components are part of a solution, so you always have a solution. I mean, we create subinstances with parts of solutions, so you have feasibility because you always have a solution. Maybe not the optimal solution, but you have a solution. I mean, the subinstance is created with pieces of solutions. Pieces of solutions, no optimal solution. Pieces of solutions. So you always generate a solution, take all the pieces, and put in the back. Generate another solution, take all the pieces, put in the. So it's not unfeasible because you always have a solution, even when it's not optimal.
But why don't you know that these pieces are optimal?
No, you know they're optimal. There are no guarantees.
But even for this subinstance, it's not optimal.
Well, for the subinstance, you are sure you are reached the optimal solution. Yeah. For the suboptimal, you are using the simplest. So you're sure that for the subinstance, you get the optimal solution, the global optimal. Yeah. For the subinstance, yeah. But not for the global, not for the original instance.
What you did your algorithm reminds me two things, two kind of algorithms that I like very much. By the repetition thing, it reminds me the uncolonial algorithm. It's hard for me, okay, but there are some reminiscences.
In fact, you can consider that each solution that you create with the uncolony, it's a greedy solution. In fact, it's a greedy solution. Okay, it's a greedy solution. And at the end, with the AND, what you have is a method to combine, to share information between this solution in the graph of the AND.
Yeah. And another thing that it remembers is the penalty methods for problems with nonlinear restrictions, where you solve with a penalty parameter, you solve 3 problems where the restrictions are put together and done, and then in fact you are not solving the problem that you want, but changing the penalty parameter, you are
that's related. Yeah, I'm not familiar with that, but yeah, they're related. At some point related. Well, in fact, when you use branch and bound, branch and cut, when you have many constraints, what you do is to delete some constraints and start solving, and then adding constraints and these things. Okay. So there is no more. Okay.
What about if you have multiple solutions?
Yeah, that I think that could be a problem, and I don't know how it would be a problem. It's not clear how do the algorithm how would the algorithm work with multiple solutions? Because you have different components that they appear in different optimal solutions. So that's difficult because you should need to, if you find several, you should need a way to say, well, but if the simplest can give you probably several optimal solutions. So you can, in that sense, there is no problem.
So maybe, I don't know if you can just add like all the optimal components of what the solutions are.
Yeah, we could, no, I mean, you have them in the, I mean, you have them, some of them, but not all of them. Yeah, I don't know, but it's an interesting question. That's interesting.